Hello friends, today I am again back with the Atomic Series Part 4 video lecture. So till date I have presented you 3 lectures, that is Part 1, Part 2 and Part 3 of atomic structure. And I hope that through these 3 lectures I could give you some ideas regarding the development of atomic structure. So it all began with the cathode experiment, which led to the discovery of electrons and protons. Later on, 1932, neutron was discovered. Then came Rutherford's scattering experiment. Then came the Planck's quantum theory. And Einstein applied Planck's quantum theory to explain the photoelectric effect, for which he was awarded the Nobel Prize for Physics. And the story continued. And the story was further carried by Niels Bohr, and who was a student of Rutherford. So in today's lecture, I'll be discussing Bohr's theory. I'll be discussing how Bohr could explain hydrogen spectrum. Then I will give you some ideas regarding the wave mechanical model of atom. And it started with the famous de Broglie hypothesis and so. So let us go to our main course. So here we are, atomic structure, part 4, myself, Vedanta Kumar Bohra, Associate Professor, Department of Chemistry, TR College, Assam, India. And you can also mail me in vedanto69@gmail.com. So if you have any difficulty in understanding my lecture, or if you have any other queries, then you are most welcome to mail me, and I will definitely reply you and try to clarify your doubts. So last class we discussed Rutherford's atomic model, which is also called the Rutherford's nuclear model of atom, because it was Rutherford who first introduced the term nucleus, and he indicated that each atom contains a heavy positively charged body called nucleus at the center, and around the nucleus the atoms revolve around. But the difficulty was that according to the theory of electrodynamics, when electron revolve around the nucleus, it will continuously lose energy and it will become weak and it will come closer to the nucleus, and ultimately it will follow a spiral path and it will fall into the nucleus. So such an atom, it will continuously lose energy, and that means we should get a continuous spectrum for hydrogen gas or any other atom. But they have found that hydrogen gas does not give a continuous spectrum, and in fact it gave line spectrum. That means hydrogen gas, it emitted only some discrete frequencies. It does not emit all types of frequency. It does not emit all type of electromagnetic radiation. It emits only certain electromagnetic radiation, and each electromagnetic radiation has certain wavelength, and they will give a corresponding spectral line in the spectrograph. So Rutherford was not able to explain the line spectrum of hydrogen, nor he was able to explain the stability of atom, because the Rutherford's nuclear model predicts the atom will be highly unstable, because a time will come when the electron following the spiral path will drop into the nucleus. So just a model of atom is highly unstable, and moreover Rutherford could not explain the line spectrum for hydrogen. In fact, Rutherford's nuclear theory predicts a continuous spectrum. So it was it was up to Niels Bohr, and who was a student of Rutherford to carry forward the story of atomic structure. Now, first of all, I will have to explain you what is a continuous spectrum and what is a line spectrum. So here it is an incandescent solid. It is a solid which upon heating will produce light. So most common is our electric bulb, because the normal electric bulb, it contains a tungsten filament, and when electric current is passed through, tungsten has got very high resistance and it get heated up and it start emitting light. And if this light is allowed to pass through a slit, and then it is allowed to travel through a prism, and the prism will disperse light and it will produce all the 7 colors. And this is called a continuous visible spectrum, because here we have continuously all the 7 visible lights: violet, blue, green, yellow, orange, red, which you call it as a vibe code. So in a continuous spectrum, we have all the electromagnetic radiations appearing in the spectrograph in continuous manner. But if you emit the spectrum of a gas, if you take a gas, you apply a high potential difference, or if you heat the gas, then what will happen? It will emit electromagnetic radiation, and this radiation, when it is passed through a prism, here you see you are not getting all the colors, you are getting only certain colors. This is a continuous spectrum because all the colors are present in the spectrum, and here you can see it, all the colors are not present, only certain colors are present, and each color will appear as a line in the photographic plate in which you have recorded the spectrum. And such kind of spectrum which will get only certain discrete frequencies is called a line spectrum. So light from incandescent solid, liquid or dense gases produces a continuous spectrum as atoms interact to emit all frequencies of visible light. So the atoms constituting this type of solid, which is emitting light when heated, it is emitting all different types of electromagnetic radiation, and consequently you are getting a continuous spectrum. But when you take a gas of very low density and you try to record the spectrum, then you will find that you are not getting a continuous spectrum. That means all the 7 visible lights are not appearing. In fact, you are getting only certain light, and each light represents a line in the spectrum, and it is called a line spectrum. So here, this is a line spectrum for hydrogen gas. So if you take hydrogen gas in a discharge tube and you pass a very high potential difference or apply a very high potential difference, then it will start emitting light. And if this light is studied by dispersing through a prism, you will find that this light contains certain frequencies. Some frequencies will be in the ultraviolet light, some will be in the visible light, and some will be in the infrared light. And each line represents an electromagnetic radiation having certain frequency or certain wavelength emitted from hydrogen gas. And such a spectrum, it is called a line spectrum. Here you can clearly see certain line, and each line represents a particular electromagnetic radiation having particular wavelength or particular frequency emitted from hydrogen gas. And some of these frequencies are in the ultraviolet region, and they are also called the Lyman series. And some of the electromagnetic radiation emitted by hydrogen gas is in the visible region, and they are also called the Bohrs series. And many radiations which are emitted from hydrogen gas is in the infrared region, and they are classified as Paschen series, bracket series, and Paffen series. So Rutherford could not explain the line spectrum of hydrogen. So it was up to Niels Bohr, who tried to explain the hydrogen spectrum based upon certain postulates, and these postulates are collectively called the Bohr atomic theory. So basically the Bohr's theory contain 3 postulates. So I will discuss one by one. Okay. So what is the first postulate? So Bohr, he used the word orbit. So just a recap of Rutherford's nuclear model. So Rutherford postulated that atom comprises of a nucleus and the electron revolve around the nucleus, and so there was no restriction regarding the path of the nucleus. That means electrons revolve around the nucleus at any path, in any path. It can take any path to revolve around the nucleus. But Bohr put a restriction upon this theory. So Bohr postulated that electron can revolve around the nucleus in an atom in selected circular path called orbit. So Rutherford did not use this word selected. He postulated electron revolve around the nucleus in circular paths. That means the electron can choose any path around the nucleus. But Bohr put some restrictions, and he postulated that electron will revolve around the nucleus only in some selected circular path which were called orbit. So the word orbit was introduced by Bohr. And what is an orbit? The orbit is a selected circular path around the nucleus in which the electron can revolve. Each orbit is associated with definite energy and are called energy level. So the electron which is in the orbit closest to the nucleus, we call it the first orbit. So the electron, when it is present in the first orbit means the orbit which is closest to the nucleus will feel the highest attraction because the nucleus is having positive charge and the electron will having negative charge. So positive charge attracts negative charge. The nucleus attracts the electrons, and as a result, the electron closest to the nucleus, that is in the first orbit, will have least energy. Then the electron in the second orbit will experience little bit less attraction by the nucleus because the Coulomb attraction decreases with distance. So as the distance between the electron and the nucleus increases, attractive force decreases, and as a result, the energy of the electron increases. So the first orbit is the orbit which is closest to the nucleus, and in the first orbit, electron experience maximum attraction, and so it has got the least energy. So electron in the second orbit, it will experience slightly higher energy, it will experience slightly lower attraction because the distance from the nucleus is increasing, and its energy will be slightly higher. So each orbit will have definite amount of energy, and the energy increases as the distance of the electron in the orbit or the radius of the orbit increases, because Bohr introduced the term orbit for circular path. So the radius orbit with the lowest radius is the orbit closest to the nucleus, and as the radius of the orbit increases, then the electron present in those orbit will experience a less attractive force and their energy will increase. So as we move away from the nucleus, the energy of the orbit will increase and the electron present in this orbit will also increase. Then Bohr put a restriction that when an electron revolves in an orbit, now what is an orbit? It's a selected circular path. Then the angular momentum of the electron in the orbit will be an integral multiple of h by 2 pi. What is n? It may have value 1, 2, 3, etc. N cannot be a fraction. H is Planck's constant. M is the mass of electron. V is the velocity of the electron in the orbit, R is the radius of the orbit. So when an electron revolves in an orbit, then the electron will satisfy this relationship. M here, that is the angular momentum of the electron, M mass of the electron, V velocity of the electron, R radius of the electron is nh2 pi by 2 pi, where n may be 1, 2, 3, etc. So when n is equal to 1, it is the first orbit. When n is equal to 2, it is the second orbit. When n is equal to 3, it is the third orbit. And if n is a fraction, then that circular path cannot be called as a orbit. So for an orbit, n must have an integral value. It must have value 1 or 2, 3, 4, etc. N cannot be a fraction. Then Bohr suggested that when electron revolve in this orbit, it does not emit radiant energy. That means when electron revolve in the orbit, it will not lose any energy, nor it will gain any energy. And so they're also called stationary state. So I think these 2 points are clear. So first of all, Bohr postulated electron will move around the nucleus only in selected circular path called orbit, and these orbit have definite amount of energy. And for an orbit, m here is equal to nh by 2 pi, m mass of electron, v velocity of electron, r radius of the orbit, n it will be an integer 1, 2, 3, etc. h is the Planck's constant. And secondly, Bohr postulated when electron revolves in an orbit, when electron moves in an orbit, it will not lose any energy, nor it will gain any energy. So they are also called stationary state. Then third postulate, that already I told you, that orbits have different amount of energy. So when the radius of the orbit increases, the energy of the electron in this orbit also increases, because when the radius increases, the attractive force between the electron in the particular orbit and the nucleus start decreasing. So Bohr postulated that when an electron jumps from one orbit to another orbit, then it may either emit energy or either it may lose energy. So when it jumps from lower orbit to higher orbit, so lower orbit, low energy, higher orbit, high energy. So when it jumps from lower to higher orbit, energy will be absorbed. And conversely, when electron jumps from higher orbit to lower orbit, that means from outer orbit to inner orbit, then it will lose energy in the form of electromagnetic radiation, or it will emit quanta. So the lowest energy state is known as the ground state. So these are basically the 3 postulates of Bohr's atomic theory. The lowest energy is known as the ground state, and the high energy states are known as the excited state. So this is the Bohr's atomic model. So these are the different circular path, and this is the first circular path. This is the n is equal to 1. It is the first orbit. This is the second circular path, n is equal to 2. This is the second orbit, and this is the third circular path, n is equal to 3. So n represents the number of the orbit. So if n is equal to 1, first orbit, it is a small radius, it is closest to the nucleus. N is equal to 2, the second orbit. N is equal to 3, this is the third orbit. So the size of the orbit increases as we move away from the nucleus. So already I told you, electron in a higher orbit will have higher energy because it will experience less attraction, and electron in a lower orbit will have lower energy. So when an electron jumps from higher orbit to lower orbit, or electron jumps from an outer orbit to an inner orbit, then the difference of energy, here in this case E3 minus E2, E3 energy of the third orbit, E2 energy of the second orbit, E3 is greater than E2. So the difference of energy E3 minus E2 will be released as a photon. So electrons can have only specified quantized energy value. Light is emitted as electron moves from one energy level to low energy level. The energy of an orbit is given by this formula, En is equal to minus RH 1 by n square. So what is RH? It is called the Rydberg constant for hydrogen atom. So for first orbit, n will be equal to 1. So n is equal to 1. Then E1 will be equal to minus RH. RH is called the Rydberg constant for hydrogen atom. And it is a value of 2.18 into 10 to the power of minus 18 joule, or 109700 centimeter inverse, or minus 13.6 electron volt. Now you can ask me why the electron energy is negative. Because we consider the energy of a free electron, that means electron which is not under the attraction of the nucleus, it has energy 0. So once the electron get into the atom, it will experience nuclear attraction, and attraction will always lower energy, and as a result energy is taken to be negative. That means the electron in an atom, inside the atom, is having lower energy than a free electron. So electron is very stable inside an atom rather than being a free, because we are arbitrarily choosing that the energy of a free electron is 0. So when it get inside an atom, immediately the electron will experience nuclear attraction, and this nuclear attraction will lower its energy, so energy is taken to be negative. So this is the Bohr's model. So this is the nucleus. Let us say this is the nucleus, and these are the different orbits. And Bohr introduced orbit as selected circular path. So here you can see n is equal to 1 means first orbit, n is equal to 2 means second orbit, n is equal to 3 means third orbit. So when an electron jumps from higher to lower orbit, higher orbit, it has high energy, lower orbit, it has got low energy. So the difference of energy will be emitted in the form of a photon. And we say this is a relaxation process. The electron is relaxing. It is giving away energy. So it is more comfortable at lower energy. Similarly, when an electron jumps from a lower orbit to a higher orbit, so this is a lower orbit, this is a higher orbit. Here there is lower energy, here there is high energy. So when it jumps, it will absorb electromagnetic radiation. It will absorb a photon, because already we know that from Planck's quantum theory that light is made up of energy packet called photon. So when an electron jumps from a lower orbit to a higher orbit, it will absorb an energy photon and it will undergo excitation. So again, this is the same thing. So this is a higher orbit, this is a lower orbit. So when an electron jumps from higher to lower orbit, it will give away energy in the form of electromagnetic radiation. So this is how hydrogen spectrum is recorded. This is a discharge tube where you take hydrogen gas, and it is subjected to a very high potential difference. And once you subject hydrogen gas to a very high potential difference, the only electron in hydrogen atom, in the ground state, it remains in the first orbit. But once you subject it to very high potential difference by applying a very high voltage in a discharge tube, the electron will get excited. That means the electron in hydrogen atom, basically which is in the first orbit in the ground state, when subjected to a high potential difference, will jump up to higher orbit and it undergo an excitation process. And in the de-excitation process, in the higher energy state, the electron will be unstable, so it will drop back to lower orbit. And when it drop back to lower orbit, it will emit photon. It will emit electromagnetic radiation. So this is a discharge tube, and here you are taking hydrogen gas, and you are subjecting it to a very high voltage, and the electron will get excited. And the excited electron will be unstable. it will drop back, and in the process it will emit electromagnetic radiation. And this radiations is allowed to pass through a slit. Then it is dispersed by a prism, and the prism will disperse the light into various components. And if you place a photographic plate, the light will damage the portion of the photographic plate it strikes, and you will get discrete lines like this. And this type of spectrum, as I already tell you, it is called a line spectrum. So this is the line spectrum for hydrogen atom. So this is in the visible region. So visible region, you already know, it is between 400 nanometer to 700 nanometer. So here you can see only 1, 2, 3, 4 lines. That means only 4 different frequencies are emitted. And in addition to this, some frequencies will be emitted below 400 nanometer, which is in the ultraviolet region. And some frequencies will be also in the infrared region, which is above 750 nanometer. Now, Bohr was able to explain this line spectrum. So here this is the figure. So these are the different orbits. And each orbit is having definite amount of energy. This is orbit number 1, n is equal to 1. This is orbit number 2. This is orbit number 3. This is orbit number 4. This is orbit 5, etc. So normally in the ground state, the electron is here. It is in the first orbit. So when you apply a suitable electromagnetic radiation, then the electron will get excited. It may move to second orbit, it may move to third orbit, it may move to 4 orbit, etc. Because when you speak of hydrogen gas, so at very less density, still there will be millions and millions of hydrogen atoms. And each hydrogen atom will undergo different type of transition. In some, the electron may get excited to the second energy level. In some, it may excited to the third energy level. And in some atom, it may get excited to the 5th energy level, so and so. So in the de-excitation process or the relaxation process, the electron will drop back to low energy level. And when the electron drop back from high energy level to the first energy level in the relaxation process, then you get electromagnetic radiations emitted in the ultraviolet region, and these lines are called Lyman series because they were studied by Lyman. Again, the electrons from higher energy state may drop to the second energy level, and in this process light will be emitted in the visible region. So here I am showing it by different color. So this is the first line. This is the first line. First line will be of low frequency, that will be towards the red radiations, because red in the visible radiation, red light has around 700 nanometer. So it is the high wavelength, means low frequency. So this is the first line from n is equal to 3 to n is equal to 2. You can see the energy gap is small. So the photon emitted will have very less frequency. So it is a red line. Then electron may drop from 4th orbit to the second orbit. So this transition is slightly bigger transition. The energy gap is higher. Still, it is in the visible region. So the electrons may drop from higher orbit to second orbit, and in this process, energy is emitted in the visible region, and these lines are called the Bohrs series. An electron may drop from higher orbit to third orbit, higher orbit to fourth orbit, higher orbit to fifth orbit, and these transitions are observed in the infrared region. That means when an electron jumps from fourth orbit to third orbit, or electron jumps from fifth orbit to fourth orbit, or electron jumps from 7th orbit to third orbit, the radiations are in the infrared region, and these radiations are, these lines are called, this is called a Paschen series, this is called a bracket series, and we have another Paffen series, and they are observed in the infrared region. So this is the energy of photon emitted. It is equal to the difference of energy. It is the energy of the F minus E. So the energy of the higher orbit minus the energy of the lower orbit. So this is the equation, that is the energy of an electron in the orbit is given by minus RH. Already I told you this is the Rydberg constant for hydrogen atom, 1 by n square f. Nf represent the number of the orbit. So you can easily calculate it. So the difference of energy, EF minus EI, EF minus EI, that is the higher orbit, this is lower orbit, it is equal to delta E. And if you do it, you will get this equation. And this equation is called the famous Rydberg equation. So delta E is equal to h nu, you can do it. So this is the diagram for hydrogen atom. This is the first orbit and its energy is minus 13.6 electron volt. Second orbit minus 3.4 electron volt, etc., etc. So as we move to higher orbit, the energy of the electron increases. So when it drops from higher orbit to lower orbit, it will start giving out the difference of energy in the form of a photon. So when an electron jumps from the third orbit to the second orbit, then the radiation emitted will be equal to 4.6 into 10 to the power of 14 Hertz, which is the frequency of red light, so and so. So this is how fluorescent light works. So we are using tube light. This is the similar thing, it is happening there. We are exciting the electron, and in the relaxation process, it will drop from higher orbit to lower orbit and it will start emitting light. So this is how Bohr tried to explain hydrogen spectrum. So Rutherford was not able to explain the hydrogen spectrum, and moreover Rutherford's nuclear model was unsatisfactory to explain the stability of atom, because the electron will follow a spiral path and drop into the nucleus, and moreover such an atom will continuously lose energy. So we expect a line spectrum for hydrogen, but for hydrogen we get line spectrum, we expect continuous spectrum if you go to the Rutherford's nuclear model of atom, but actually we get a line spectrum. And so Bohr used the idea of quantization of energy as postulated by Planck in Planck quantum theory, and he could propose a theory for the structure of atom based upon 3 postulates. And based on these postulates and Planck's idea of quantization of energy, he could explain the line spectrum of hydrogen. So friends, I hope today I could give you some ideas regarding Bohr's theory. And as promised, if you have any query, you can mail me and definitely I will help you. And for today, I'll be stopping here. And if you're really liking this video, you please subscribe my channel. And with the concluding lecture, we'll be back. That is the part 5 lecture of atomic structure. I'll be back, where I'll be discussing the wave mechanical model of atom. So till then, it is goodbye. Have a good day.